At first mention, we often hear that plate tectonics is like a hard-boiled egg with a cracked, immovable shell where the pieces slam into each other, or like the skin of an apple, and it's slipping around the fruit with the skin crinkling as it collides. I heard it was like a football game where 7 plates that float on the mantle bash and smash into each other, or even cars in a demolition derby. Each of these analogies serve their purpose by simplifying and removing reality, but the problem is, plate tectonics is like plate tectonics, uber dependent on chemistry, the angles of collision and separation. We study plate tectonics by observing their interactions above and below the surface in the anatomy, the change in motion and shape over time, and their influence on ecosystems, people, and life. Small changes in chemistry or the age of a shell can be the determining factor between colliding plates forming a volcanic island chain like Japan or a large mountainous region like the Himalayas. No need to memorize the thickness and densities just yet. I put them here to begin your familiarization. Where plates first cool and form, we call this the crust. Continental crust ranges in thickness from 35 to about 100 kilometers and is relatively light in density. Oceanic crust is much more dense, but thinner, ranging only about 7 to 10 kilometers thick. The crust is part of the lithosphere, the solid rock sphere of Earth. As a crust ages, the plasticky upper part of the mantle, the asthenosphere, cools and crystallizes on the underbelly of the crust. The lithosphere thickens with age from the accumulation of these crystals, increasing in density as it ages. Observing differences between oceanic and continental lithosphere prepares us to understand that thickness originates in existence. Where the stuff smashes together, these often begin as oceanic plate collisions because continents are usually surrounded by oceanic lithosphere. The older oceanic plate will subduct because the lithosphere is thicker, it's older, and it's denser, so it'll sink. At depth, the water is pressurized out of the plate. Such an increase in water at a specific area melts part of the plate and mantle. We call it partial melting, and it occurs when the system only slightly changes, allowing a small portion to melt. Continent-continent collisions build mountains like the Himalayas or the Great Alaskan Range, scooping up all sorts of material at the continent-ocean margins, creating a suture. It's often made of the crust, lithosphere, and sometimes the asthenosphere. Interesting note, over Earth's history, the subducted volume roughly equals the erupted and mountain volumes. Kind of nifty. There's a certain anatomy to a convergence zone. Let's begin in the trenches. These are depressions marking location of subduction. Trenches are perpendicular to the direction of plate motion. So as the downgoing plate moves in this direction, the trench will form in the perpendicular direction. But the trench also is parallel to pretty much all the other features. Accretionary prisms are wedges of sediment scraped from the ocean floor of the subducting slab. These often bury the trench axis from obvious sight. And these mud slabs that are kind of accreted as wedges that almost look like an orange or a piece of fruit are really well put together up here in this image. A forearc basin is forced by the drag on the overriding plate. A great example is California's Central Valley. The basin can also be a long lake or part of an ocean, but is always found parallel to the collision and just before the volcanic arc. By the addition of water from the subducting slab, low melting point minerals melt and migrate up through fractures and weaknesses in the overriding plate to either cool or, in most cases, erupt as volcanoes. Volcanic arcs on the continents, as shown here, create ranges like the Cascades or the Sierra Nevadas of Yosemite National Park when California's Central Valley was a forearc basin. Volcanic arcs on ocean floors, however, create island arcs like Japan. Weak crustal layers fault and fold to build mountains. If this compression occurs before the volcanic arc, we might see a range along the coast that we call a coastal range, or, as seen here, a back arc range. Earth shapes through weaknesses responding to stress. This is why we say that all of Earth's faults are stress-related. Alright, time for a quiz. Pause the video and practice the convergent anatomy, which we just covered, by answering the following questions. Alright, so let's move on. You may remember these boundaries as spreading centers when you first learned about them. They begin at the weakest location, where tension thins the plastic lithosphere at depth and faults the brittle crust at the surface. Mapping faults in the field, we've come to learn they begin with high angles, but take a quick oblique scoop into a low angle, usually following some sort of weak layer of rock. Further rifting allows sliding of these blocks, such that they come to lay on their sides with large basins separating them. At this point, the blocks are tall enough to create mountain ranges. We call such early rifting provinces basin and range. The depressurization of the mantle causes the rift to rise up, which encourages more rifting and further separation of the blocks. Eventually, volcanoes will erupt. The mantle, having followed fractures and weak planes, rises up through the lithosphere, just as seen in convergence. These volcanoes can be explosive and often make cones. Finally, the continent separates, and we observe rift volcanism, where crust splits and lava straight from the mantle bulges out in pillow-like shapes. This occurs in the valley of the rift, seen at the top of the ridge. Note that at the rift there is no lithosphere accumulation because the ocean crust is just newly formed. The lithosphere will accumulate and crystallize from the asthenosphere with time as the crust gains age and distance from the rift. Let's take a little bit closer look at this time 5. Without much crust, the mantle easily bulges up and erupts the rock we call basalt, forming ocean crust. As the asthenosphere crystallizes to the crust on both sides, making the lithosphere thicker, the ocean crusts are weighed down and pulled in opposite directions off the mantle bulge, further promoting divergence and rifting. The Nevada region comprises a large early rift system where the basins of sediment and ranges of faulted blocks identify the tension currently thinning our continent. Both pointy explosive volcanism and early rift basalt erupt across this region. Recall that we name geologic provinces like this a basin and range. Eventually, maybe in about 10 million years, our continent will split and look much more like Africa, with very long lakes through this region. A stepping stone, bound by water, exists between Africa and the Arabian Peninsula, as Africa slowly rotates clockwise to close the Mediterranean. The plate rips like a piece of paper, with the Sinai Peninsula stuck at the head of the tear. Within the Gulf of Suez, the rift periodically erupts new basaltic ocean crust. Note the arrows showing plate direction in the Gulf of Aqaba over here in the image of what a geologist sees. The difference in rift speeds forces one section to move faster than the other. This is a transform boundary, and it's our final boundary. Transform boundaries occur where plates slide or smear against one another. This occurs if plates slide in opposite directions or even just at different speeds. They're common at divergent boundaries where the rifts are offset, just as we saw in the Gulf of Aqaba and as we see here. First, I want you to note the continental margin of plate A and plate B. The margin is where the continent meets the ocean. This offset is caused by the offset in the divergent ridge, these spreading centers, and in this little overlap we have a transform boundary. The plate motion here is parallel, but if the plates have a slight convergence, mountains can form. Transform boundaries are also known to produce trenches when slightly diverging, and massive earthquakes if their boundaries are jagged. Let's take a look at that. Hopefully this image looks familiar because this is just a different angle of the same location used in the convergent quiz. Can you spot the transform boundary now? Here's a little help. And where there's a boundary, there must be plates and motion. These are all speeds with respect to the mid-Atlantic ridge. Removing the boundary line and instead using the speeds, you should be able to identify that Cuba was once attached to Haiti and that Belize and Guatemala, over here, once lay much more just to the north of Honduras. You can also probably mention many other things. And so Take a moment, maybe even pause the video, and try and hypothesize and explain, how did these plates evolve to do this? Alright, most plates move because a divergent zone is pushing them. Yet, most plates aren't like the Caribbean plate. They don't move in the same direction and share starkly similar features like this line of Cuba to Haiti and the Dominican Republic. Nor do they often share a dot of islands that are probably all smears and been ripped off from the South American plate as the two smear along each other. The Caribbean plate moves in the same direction as the North and South American plates because it was once a part of them. About 50 million years ago, the Caribbean plate began resisting motion. It became difficult to move. Maybe there was some sort of blockade over here in this convergent zone. I don't really know. Its slow progression caused subduction of the North American plate on the east side, causing this massive accretionary prism right over here and this chain of volcanic islands, this volcanic island arc. The bend in the plate at the Dominican Republic causes a slight compression, forming mountains and shearing. Can you use this to explain why earthquakes occur around in Port-au-Prince, Haiti? Over here, opposite of the compression, we find a trench where the North American plate is trying to stay above the mantle and stop from sinking. And then opposite of the compression over here, we find an extensional zone where there's a tiny trench of separation. In this tiny little trench, this is a divergent zone, and eventually we will find rift volcanism, mantle coming up to just bubble and bulge. There are many purposes to justify a study of plate tectonics. Resolving or gathering the details can help you forecast or even explain landforms and properties. And as always, good science raises more questions than it answers. I hope next time I see you, your list is long with many, many questions for which you need answers.